All right, let's get started. So today I'm going to introduce the Optimism Bedrock, and it'll be a little bit technical because I want you to know the implementation details, so you can have all the details about how they implement a layer 2 system. And if you're not familiar with those techniques and codes, it's okay. I think you can still learn a lot about how the optimism works. So firstly, I'll introduce what is optimistic rollup. Optimistic rollup is a layer 2 scaling solution for Ethereum to provide faster transaction times and lower fees. They bundles the transactions on layer 2 into batches and submit them on Ethereum mainnet for data availability. And the execution results, we call them state roots, are submitted on layer 1 for verification. So we can reduce gas fees and network congestions because these layer 2 transactions were not executed on layer 1. They just submitted on layer 1. They actually executed in another environment. We call that layer 2. So we can save a lot of gas because execution transaction on layer 1 is expensive. And we want to ensure that layer 2 system is secure. And for here, secure means that data availability and data integrity and the result correctness and verifiable. So we submit those transactions on layer 1. So those transactions could always be retrieved through a Ethereum RPC call. So the data is available all the time because there are so much Ethereum nodes around the world. And Ethereum can use some cryptographic mechanism to ensure that the data is correct. So we can also ensure the data integrity. And these two conditions, no matter you're using optimistic rollup or ZK rollup, we use Ethereum mainnet to ensure that data is available and data is correct. The third condition is that we ensure the layer 2 transactions result is correct and verifiable. So for optimistic rollup, we need to trust that someone submit the state root of the layer 2 chain is correct. So we need to trust them optimistically. But the result is verifiable. So someone can challenge that a state root is wrong. We can challenge that on layer 1. This is what optimistic rollup achieve the result correctness. For ZK rollup, they use ZK knowledge to ensure that the result is correct and also verifiable. Because we trust the state root optimistically, the time period for fraud proof or we call fraud proof is around 7 days. So it will take 7 days to ensure that a state root is correct because no one will challenge the state root in these 7 days. And then we can call this state root is safe. And the challenge can be interactive or non-interactive. In Arbitrum, they use a interactive process. And in Optimism, the first version of Optimism is called OVM v1. They use a non-interactive process to do the fraud-proof challenge. But then they think it's not a good. I think it's not a good approach to do the fraud-proof challenge. So they transfer the non-interactive challenge to interactive one. I'll introduce those parts later. A brief history of Optimism. The first version is OVM v1. OVM v1 use a non-interactive fraud-proof system that execute a layer 2 transaction on layer 1. So there will be a sandbox environment on layer 1 that can execute a layer 2 transaction. And in OVM v1, the contract on the OVM v1 is using the OVM backcode. So we need to execute OVM backcode in EVM on layer 1. We can call this OVM in EVM or EVM in EVM. There is a very detailed article about how the OVM v1 works, written by the CTO of Paradigm. It's a very good article. If you want to know the details, you can read this article. There are some takeaways for the OVM v1. OVM v1 is not EVM compatible because when we write contract, we use Solidity language. Solidity compiles to EVM on the mainnet. But if we want to deploy this contract on OVM v1, we need to use another compiler to compile Solidity codes into OVM backcode and then deploy them on OVM v1. So what is the OVM backcode? Actually, it is same as EVM backcode, but some OP code are replaced by OVM. Those OP codes are related to the execution context. For example, I want to know the caller of the contract. So we have a caller OP code. Caller OP code will be replaced by a OVM OP code. And we want to read or write to the storage of contract. This two OP code will also be replaced by two OVM OP code. And if we want to get the timestamp of the layer 2 block, this timestamp OP code will be replaced by OVM timestamp. Why we need to replace these OP codes? Because when we execute the layer 2 transaction on layer 1, in the fraud-proof system in OVM v1, the layer 2 transaction has to be executed on layer 1. So in the layer 1, you get another, if you call this timestamp OP code, you'll get the timestamp on layer 1 instead of layer 2. So the transaction on layer 2 needs to know the timestamp of the layer 2 system. And if we use sload or store, we need to load the state in layer 2 instead of layer 1. So they replace this OP code to some OVM OP codes. What is this OVM OP code? It's actually a function call. So it is also EVM OP codes. So in this article, they have some example. Yeah. So in the EVM, you use sload to load a storage in the contract. And in OVM, this sload will be replaced to the OVM sload. What is OVM sload here? Actually, OVM sload is just called a function called OVM sload. And here called the target is the caller. So there will be an execution manager that helps to maintain the execution context. So the contract is actually called by the execution manager. So he will ask for the execution manager to load some storage of this contract. So on layer 2, they intersect this function call and load the contract from the Ethereum node on layer 2 in the state DB. If this transaction got executed on layer 1, there will be an execution manager contract in layer 1. So this transaction, when this transaction got executed on layer 1, he will call the execution manager contract to ask to load the storage on a layer 2 contract. So how does the execution manager know what is the value of this slot? The value should be uploaded by user manually. So this is how they replace the OP codes. And I will not go into too much details about this implementation because OVM v1 is already deprecated. If you want to know more, you can read this article. And the fault proof is non-interactive. Non-interactive means the whole transaction is replayed on layer 1. So all the instructions in this transaction will be replayed in layer 1 in a sandbox environment. The sandbox environment is the execution manager here. So the execution manager maintains the context of the transaction. So he can know the storage in a slot or the timestamp of a layer 2 block or the caller of this transaction on layer 2. Because we replaced a single, here it replaced a single OP code to multiple OP code. So the contract size limit get hit faster on OVM v1. In Ethereum mainnet, contract can be up to 24 kilobytes because we need to replay layer 2 transactions on layer 1. So all the contracts on layer 2 are also limited to 24 kilobytes. But if you write in Solidity code, when you get compared to OVM, it will end up bigger than it was in EVM because some EVM OP code are replaced to multiple OVM OP code. For example, a single S-load OP code will be replaced to multiple code. Here is the call function. So the contract size will be bigger if you compare to OVM. So it's harder for developers because sometimes we just write a contract and fit into 24 kilobytes in EVM. When we compare it to OVM, it will exceed this limit. So we have to optimize or refactor the contract. So it's not very convenient for developer. We need to manage the contract size, and we need to use another compiler to compile the Solidity code to OVM bytecode. And some tools are not compatible. So there are a lot of disadvantages of this version. And layer 2 transactions are batch submitted to layer 1 in the contract storage. So they submit the layer 2 transactions to a contract on layer 1. So you have to store those data in the contract storage instead of core data. It would be expensive to save transactions in a contract storage. But in later version, they will use core data. So we don't need to store the layer 2 transaction in the storage. We just store them in the transactions core data. They do this in OVM v1 because of some restrictions of the EVM in EVM or OVM in EVM. So it's gas wasting, and we cannot compress the layer 2 transactions because in the contract, you cannot do the decompression. So there are a lot of disadvantages in OVM v1. Then they upgraded to OVM v2, and they introduced the EVM equivalence. EVM equivalence means that they want to be compatible with all of the components in the ETH mainnet. So it would be, and every debugger, every toolchain, every node implementation will be seamlessly migrate to layer 2 system. So the contract now don't need to be compiled to OVM bytecode. It's just EVM bytecode. So we don't need to use another compiler to compile our Solidity code, we can use the official compiler because the contract on layer 2 is EVM compatible. So all the opcodes are the same as the EVM opcode on layer 1. And it's also compatible with the ETH API so that all these clients can be reused on layer 2. You just need to change the RPC URL and the chain ID. And all the developer tools and frameworks can be reused. So for developer, it would be better because it's providing a seamless experience for us. And the fault-proof system is not implemented in this version. So we have to trust that Optimism team, they won't do fraudulent activities because of the legal concerns. Yeah. But technically, they can rug pull all the money in the layer 2. Yeah. But there's a difference between ETH mainnet. In this version, in the layer 2 block, there is only one transaction. But in ETH mainnet, a layer 1 block can contain multiple transactions. So this is what is EVM equivalent rollup means. So they are compatible with all the infrastructures in the ETH mainnet. And the next version is Bedrock. And Bedrock is already deployed on the testnet, Gorilla testnet, and will be deployed in the mainnet later this year. And the design goals of Optimism Bedrock is that they want to minimize the code difference between Ethereum and Optimism rollup, because every single line of code you need to developers to maintain it. If you can minimize the code diffs, it will be better to maintain and following the upstream Optimism, upstream Ethereum code base. So they have a OP-Geth repository. They made only a few thousand of codes changes on the Go Ethereum client, and you can check the code diffs here. This. So they only made 2,000 of code changes on the Go Ethereum clients. And they want to reuse every design patterns on layer 1. For example, EIP 1559 or some other EIPs. And also the execution consensus layer separation on layer 1. So they reuse those design patterns on layer 1. Like the consensus execution client separation. So the OP-Geth on layer, the Go Ethereum on layer 1 mainnet is the execution layer after POS. And the OP-Geth is the execution layer of Bedrock. So it's pretty much the same to the layer 1. So the execution API and the execution API will be reused to build layer 2 blocks. In layer 1, the execution APIs are used to build layer 1 blocks, and they reuse this architecture to use the execution API to build layer 2 blocks. And they have core data compression. In the previous version, OVM v1 and OVM v2, like I said, they store the layer 2 transaction in the contract storage, and they will do some additional computation, like compute Merkle root in this contract. So it's gas wasting, but in Bedrock, those transactions are just saved as core data. They don't need to call any contract, and the core data can be compressed before submitted to layer 1. And they have accurate time steps so that it is possible to build real-time applications. And the fault proof will be implemented in later upgrade. All right. Let's take a look at the architecture of OP Bedrock. So the yellow part is some contracts on layer 1. And the green part is the component on layer 2. Here, the deposit feed is a contract that you can send a transaction on layer 1 to call a transaction on layer to call a contract on layer 2. If you want to call a contract on layer 2, you just need to send a transaction to this deposit feed contract, and the contract will be they will emit an event in this contract, and they will transform this event to a transaction on layer 2 and call the target you want to call. And they have a batch inbox contract. This this is not a contract. This is just a EOA address. So they submit all the layer 2 transactions through this batch submitter. This is a progress they run to submit the transactions to EOA address on layer 1. So the layer 2 transactions are submitted as transaction coded, and they will compress before submitted. And the rollup node reads all the transactions on layer 1 to this deposit fee contract. So they convert the events emitted in this contract to a layer 2 transaction on layer 2. And the layer 2 gas is the OP gas, as I mentioned before. It is the execution engine of Optimism Bedrock. So layer 2 blocks are produced through this OP gas. And rollup node is stateless. Rollup node don't need to save any states in the progress. All the states are stored as layer 2 blocks in this OP gas. And there is an output submitter that submit all the layer 2 states to a layer 1 contract. So let's say in layer 2, we have now the block head is at like 10,000. This is a layer 2 block, the latest layer 2 block. And the output submitter reads the state in the latest layer 2 block and submit the state to a layer 1 contract. We call that L2 output oracle. If the state is wrong, someone can challenge this state if the fault-proof system is implemented. For now, we don't have the fault-proof, so you have to trust that the output submitter always submit the correct state to layer 1. And here we have red and blue parts. The red part is the sequencer. Sequencer is responsible to, like here, submit the layer 2 transactions to layer 1 and submit the layer 2 states to layer 1. He also will collect all the transactions on layer 2 and produce blocks on layer 2. So the sequencer produce layer 2 blocks and submit the transactions and the state root result to layer 1. For now, the sequencer is run by Optimism team. I think in the future, everyone should be able to run a sequencer to achieve decentralized layer 2. But for now, it's not permissionless. The sequencer is run by Optimism's team. And if you want to run the layer 2 gas, you should be a verifier here. So you only need to run these two process, the rollup node and the layer 2 gas. By using the rollup node, you can rebuild the layer 2 node from layer 1, because you can read all the deposit from layer 1 in this deposit feed contract, and you can read all the transactions of layer 2 through this batch inbox address. And you can call the execution API of layer 2 gas to reproduce the layer 2 blocks. And you can also sync the layer 2 blocks from sequencer. There are two ways to build layer 2 blocks for verifier. And if you found the state root is not correct, for example, the output submitters submit a wrong state to the layer 2 output oracle, you can challenge those states when the fault-proof system is ready. All right, I've introduced all these parts and how the transaction and the block is produced on layer 2. This is pretty much like the above image. We submit transaction directly on layer 2, so the transaction is actually synced through this layer 2 gas process. They have a transaction pool, and those transactions will be produced to a layer 2 block by sequencer. So this is the red part because it's run by sequencer, so they would produce layer 2 blocks. And they have a batch submitter, sequencer have a batch submitter process that submit those transactions in this layer 2 block to the batch inbox contract. And we also have some transactions sent from users in layer 1. They send transactions to this deposit feed contract, and we can fetch those transactions to the rollup node and produce a layer 2 block. For a sequencer, you can produce a layer 2 block without submit those transactions to layer 1, because you can produce a layer 2 block first and then submit those transactions to layer 1. So this kind of blocks is unsafe because the transactions are not saved on layer 1. After those transactions are saved on layer 1, we can call this block is safe. Because the layer 1 may be reorged, so the blocks can be discarded and reorg. Unsafe block on layer 2 may also be reorged. But if the transactions are already saved on layer 1 and is finalized in the ETH POS, we can ensure that those blocks will not be reorged, so it's safe. And for the verifier, we can use those transactions in the batch inbox address on layer 1 and all the deposit events, and we can rebuild all the layer 2 blocks. I mean the safe layer 2 block. For the unsafe layer 2 blocks, you have to sync from the sequencer. The block derivation is the process that how the rollup node rebuild the layer 2 blocks. In Bedrock, there's a fixed time to produce a block that is 2 seconds. And the single block can contain multiple transactions. Before Bedrock, the current version on the mainnet of Optimism, they have a variable block time, and only one transaction per block. Using a fixed block time, it would be consistent with the Ethereum mainnet. On Ethereum mainnet, there will be 12 seconds for block time. So the block time is fixed on layer 1 and layer 2. And it will be convenient for developers to use block times in the contract to keep track of time. For example, the Sushi's master chef contract, they use block numbers to track the time. Because block time step is easier to be manipulated by each node, but the block number is harder to be manipulated. And because we save multiple transactions in a single block, we can reduce some overhead for storing the blockchain, because every block you need to store some states root of this block. There will be some overhead to produce a block. And we don't need to update state try roots after each transaction. And the process to derive a rollup chain only from layer 1 block is what we call derive here. So as I mentioned, there are 3 kinds of block in layer 2. An unsafe block is the layer 2 block that only knows by layer 2 rollup nodes, but the transactions in this block are not submitted to layer 1, so it's unsafe. A safe layer 2 block is that a block contains all the transactions, and those transactions are submitted to layer 1 by the sequencer. And the finalized layer 2 block means the transactions are sent to layer 1, and the layer 1 block is finalized. Finality is the term in the ETH POS. You can check this link to know the details. Finalized means that it is safe and it will not be reorged in layer 1 or layer 2. And the derived process is we can build the layer 2 chain from the ground up, only use the data in layer 1. We don't have to use any data in layer 2. We can read all the data on layer 1 to build the layer 2 optimism from the ground up. So it is safe for optimism because all the data is available on layer 1, and we can ensure that the data is correct. So anyone can build the optimism rollup chain from the ground up by reading those data in layer 1. And then it becomes the rollup blockchain in layer 2. But in this layer 2 chain, it doesn't contains the unsafe layer 2 blocks, because the transactions in this unsafe layer 2 blocks are not submitted in layer 1. So it's not updated. The latest block in this layer 2 chain may be outdated a little bit. And we have epochs and sequencing window. In Optimism Bedrock, there's a 1-to-1 correspondence between layer 1 block numbers and epoch numbers. So every block number on layer 1 means a new epoch in layer 2. In layer 1, the block time is 12 seconds, and in layer 2, the block time is 2 seconds. So technically, there will be 6 blocks during the block period in layer 1. So these 6 blocks, let's say the block number here is 10,000. This will be the epoch number on layer 2. So these 6 layer 2 blocks belongs to the 10,000 epoch. But it's not. But you can maybe have 5, 8, or 10 blocks on layer 2. It's okay because we have a sequencing window. So there's 1-to-1 relationship between layer 1 block and epoch, and each epoch on layer 2 contains multiple layer 2 blocks. Like this picture, the epoch 1 is this block in layer 1, and it contains 2 layer 2 blocks. And in epoch 2, it contains 3 layer 2 blocks. And in epoch 3, it contains like 4 layer 2 blocks. And as the example before, let's say we have a block 10,000 on layer 1. This is a layer 1 block. And this means that all the layer 2 block after this layer 1 block will belong to this epoch number. This is the epoch number in layer 2. And we have some layer 2 blocks here. Maybe we have 6 layer 2 blocks. All the transactions in these 6 layer 2 blocks can be submitted later. We don't need to submit it in the next block in layer 1, like the 10,001. We don't have to submit in this block. We can submit it later. And the sequencing window defines how you can submit those transactions to layer 1. If the second window size is, like, let's say it's 100, so we can submit these layer 2 transactions in layer 1 within this range, 10,100, within this range. This is the sequencing window of the epoch 10,000. So maybe we submit those transactions after 10 blocks. We submit in 10,010. We submit in this block. It is valid because this block belongs to this sequencing window. It applies to every epoch. For the next epoch, 10,001, the sequencing window will be 10,001 and 10,101. That is the sequencing window. So you have to wait for you have to wait at least the sequencing window. I'm sorry, you have to wait at most the sequencing window to fetch all the layer 2 transactions in this epoch, because the transactions in this epoch may be submitted in the last block of this sequencing window. So you have to wait the sequencing window ends, and you can read all the transactions of this epoch on layer 2. And the last part is the engine API. The engine API is same as the ETH POS. As we said, we have a roll-up node here. This is a separate process, and we have an engine, execution engine. This is the OPGath program. OPGath. OPGath is the execution engine, and same as the Go Ethereum is the Ethereum execution engine on the mainnet. And on the mainnet, consensus client, the beacon chain, will call the execution engine API to tell them to create blocks. And it is the same. It is the same on the Optimism Bedrock. You call the engine API. Actually, the sequencer call the engine API to produce a new layer 2 block. This is the whole process how they use those APIs. Actually, it is the same API they use as the mainnet execution engine. They just added some additional field, like additional payload attributes on layer 2. The first step is that the rollup driver of the sequencer calls the engine fork choice updated v1 to tell the execution engine to produce a new block. This API is telling that you have to produce a new block. So the engine API starts to produce a new block, and it will collect all the transactions in its transaction pool and build a new block. And it will tell the rollup node about the payload ID. Payload are used to create a new block. When the rollup node gets the payload, it will use this engine execute payload to finalize the block production. I'm sorry, the last API is used to finalize the block production. So after the last call, there will be a new layer 2 block produced by the OP-get. That is the execution engine on layer 2. And this block can be propagated in the layer 2 networks. Okay, this is the overview of OP Bedrock, and I will tell you how actually they works in OP Bedrock. So it will be more technical after these slides. So we have to have some preliminary knowledges in Ethereum. The first one is RLP encoding. It is used to encode arbitrarily nested arrays of binary data. This encoding is used very often in Ethereum's execution layer. If you want to know more, you can click this link. And the second one is Merkle-Patricia trie. The Merkle-Patricia trie is also used very often in the Ethereum execution engine. It's very like a Merkle tree, but in Merkle tree, we store a list of values, and we can prove that a single value is in this list. So we can prove a value is in a list. But Merkle-Patricia trie is like a key value mapping. So we can use it to prove that a key is in this trie, Merkle-Patricia trie. And in this key, we have this specific value. So we can prove the key and value. That is the difference from Merkle tree. Because in Ethereum, they use key value database and they use key value mappings a lot. So they use this Merkle-Patricia trie data structure. And if you want to learn the Merkle-Patricia trie, I recommend you to read this article. He has a repo to demonstrate how the Merkle-Patricia trie works. Have the repo. And the third part is what is Ethereum transaction? The structure of Ethereum transaction is as below. It contains nonce of the address, the sender address, and it contains a chain ID and gas price. I guess you are familiar with this because we almost send Ethereum transactions every day. And the gas price field, it can be replaced to this field after EIP 1995. And we have gas limit, and we have a 2 address. That means what address this transaction wants to call. If we transfer ETH, these two address may be a EOA address or contract address. If we want to call another contract, this address should be a contract address. And the value means the ETH you want to send in this transaction. The data and the input is the message you want to send in this transaction. If you want to call a function, the function parameters will be encoded in this data, or we can call it input. And we have a ECDSA digital signature of this transaction so that we can verify this transaction is valid and is actually sent from an address that is also valid. And the block header in Ethereum, this is a picture I grabbed from Google. It may be a little bit outdated, but I think it's fine because we don't need to use every single field in the block header. The most important part is that there are 3 Merkle-Patricia trie in the block header. Like I said, they use Merkle-Patricia trie to store the data in Ethereum. The first one is the state root. This word will be referenced a lot in layer 2 because we all say you submit some state root of layer 2 chain to layer 1. This is what state root is. State root is the root of the ETH account state. The ETH account states will be encoded to a Merkle-Patricia trie. And in this Merkle-Patricia trie, the key is the account address. So you can fetch the information about account by using the account address through this state root Merkle-Patricia trie. And the value contains several fields. The first one is the balance, is here, balance, announce. Balance is the ETH amount in this account. Announce is used to identify the transaction index. Code hash is used for contract. When the account, when this address is a contract, they have some contract code in this address. So they will store code hash in the account state. And we have another storage root in this account state. The storage root is another Merkle-Patricia trie. The storage root is used to store the contract storage. So in a contract, we have a contract storage slot. So the key is the contract slot, and the value is the slot value. So all the contract storage is stored in this Merkle-Patricia trie. This is the state root. So this state root contains all the information about all the Ethereum addresses or Ethereum accounts in the blockchain. And we have a transaction. Transaction root is the Merkle-Patricia trie that contains all the transactions in this block. So they build another Merkle-Patricia trie by using the transactions. In this Merkle-Patricia trie, the key is the transaction index. The value is the transaction data encoded by the RLP encoding. And we have a state root, receipt root. The receipt root is all the transaction receipts in this block. The transaction receipts contains all the events emitted in this transaction. And it's also encoded in RLP. And in this Merkle-Patricia trie, the key is also the transaction index, and the value is the receipts encoded in RLP. All right. Dig into the implementation details. Firstly, I'll introduce the deposit. Deposit means someone initiate a transaction on layer 1, and this transaction should be executed on layer 2. Deposit doesn't mean you have to deposit some money. You don't need to deposit some token or money. Deposit only means that a transaction is initiated on layer 1, but it will be executed on layer 2. So for this kind of transactions, OP defines a new transaction type in their execution engine that would use a specific prefix to specify that is a deposited transaction. And in this deposit transaction, we still have the to address. Like I said before, we still have the value is the ETH value you want to send in this transaction. And we still have the data that contains the message of this transaction. If you want to call some function, the function parameters are encoded in this data. And we also have gas limit. But there are some new fields for this deposit transaction. The first one is from. Why we need use the from? In the transaction above, we don't have a from. But how we get the from address in the transaction? Because we have the digital signature, we can recover the from address through this digital signature. But deposit transaction don't need to be signed. It's actually generated from thin air. So there isn't a signature with it. So we have to specify who is the sender. What is the sender address here? And another new field is the mint. Mint means that when the deposit transaction get executed on layer 2, you have to mint this amount of value to this address. So before the transaction is executed, the execution engine should mint some ETH to this address and then execute the transaction. In this way, we can bridge the ETH from layer 1 to layer 2. But you can also specify a 0 in this field, so you don't have to mint ETH. And since we don't have the digital signature and we don't have the nonce, like above, we don't have this nonce. So if someone calls a layer 2 contract, you can replay those transactions. If we don't have the nonce and digital signature, you can replay it because all this field can be sent. If you call target twice, all this field can be sent. So they have another field called source hash. The source hash contains the layer 1 block hash and the event index in layer 1, because the layer 1 block hash and events cannot be duplicated, so you cannot replay a deposited transaction on layer 2 again. So there will not be two SAM deposited transaction on layer 2 because the source hash will be different for each of the deposited transaction. The event index means that deposits are actually generated from an event on layer 1. I'll explain the details later. And there are two kinds of deposited transactions. The first one is system transactions. It is generated automatically by the layer 2. So in every layer 2 block, the first transaction is a system transaction. This system transaction is used to setting some attributes from layer 1, like the layer 1 gas price, layer 1 timestamp, and they set it to layer 2 contract. So the layer 2 can know the layer 1 block hash, layer 1 latest block hash, layer 1 timestamp, and the layer 1 gas price. I'll show you here. This is a Corelli optimism. You can click any layer 2 blocks in these transactions. You can see the first transaction is to set layer 1 block values. So this is the system deposited transactions. The from address is the system address. So it calls a contract on layer 2 to record the layer 1 attributes. You can see this address is that. So no one has the private key of this address. It just generated from thin air in the layer 2 rollup node. And in this call, in this system attribute call, is just to set some layer 1 attributes like the layer 1 block number, time step, and the gas price, etc. And the second type of deposit transaction is deposit by user. So some users send transactions on layer 1. They want to call some address on layer 2. So this kind of transaction is first initialized on layer 1. And in the layer 1 contract, there's a layer 1 contract, and it will emit an event on layer 1. And this is layer 1. And in layer 2, the rollup node, like I said before, OP node, we call it OP node, reads those events. So the OP node knows how many deposit transactions or how many events are emitted in a layer 1 block. And we use events to generate a deposit transaction. Deposit transaction on layer 2. So these transactions are generated by the OP node of sequencer. And those transactions will be included in the latest layer 2 block. This is how the deposit transaction got generated. And it's invalid to have a layer 2 block without including the deposit of its layer 1 block. They add this restriction to anti-censorship. So if someone want to censor address on layer 1, it would be an invalid layer 2 block. And other transactions are users sent directly on layer 2. And deposit transactions are prioritized to be included in layer 2 block. So if we want to produce a new layer 2 block, the first thing is to include all the deposited transactions on layer 1. And then we include all the transactions sent directly in layer 2. So the deposit transaction are prioritized to be included in the block. They'll be executed firstly in this block. And we can see, let me find an example for this. I think, yeah. In this block, the first transaction is the system deposit transaction. And you can see here the transaction fee is 0. That means it's a deposit transaction. And the second one is also a deposit transaction. This is a deposit transaction triggered by me. And it also has a fee, 0 fee. And then these two transactions is sent by users on layer 2. So deposit transaction got executed firstly, and then all the transactions sent by users on layer 2. And you can see the gas price is not 0 here. All right. So how the OP node generate deposit transactions? Firstly, user have to call a contract on layer 1 to specify which address they want to call on layer 2 and how much value they want to send and the gas limit for this transaction and the data in this transaction. So they have to call a contract on layer 1. This Optimism portal is actually the contract here. The deposit fee, the name of deposit fee contract is actually the deposit portal. Yeah. So first, user call contract on layer 1. And in this contract, it will emit an event called transaction deposited and it contains several fields. The from is the address on layer 1. The to is the address on layer 2. So you want to call address on layer 2 from layer 1. So the from is the address on layer 1. To is the address on layer 2. The version is the deposit transaction version. And the data contains the value and the transaction data you want to call. So they emit an event on layer 1. And if this from address is a contract, they would do address aliasing before they emit the event. And you can read this document about why they're using address aliasing they're using this address aliasing to prevent someone attack a layer 2 contract from layer 1. I can explain a little bit. For example, we have some contract on layer 2. There's contract 1 and there's a contract 2. And for this contract 2, let's say the contract 1 is not upgradable and it doesn't have an owner or admin. So the second contract can trust this contract because it's open sourced and not upgradable and doesn't have an owner or an admin. So he may approve the contract 1 to spend all the USDC he has. So he can trust him. He can trust this address on layer 2, right? But someone may deploy a contract on layer 1. Let's call this C1 on layer 1. Someone can deploy a contract with the same address with this contract on layer 2, but the contract content is different because the contract address is generated from the sender's nonce. So you can use a SAM nonce to deploy a contract in another chain, but have the contract code. The contract code is different. If that's true, and the C1 contract on layer 1 can initialize a deposit, like I was said before. He can initialize a deposit to call another contract on layer 2. Let's say he called the USDC transfer from layer 2. Because the address is the same, so he can transfer all the USDC the C2 has. So there will be a problem if we don't do the address aliasing. Address aliasing means that if the address on layer 1 is a contract, you have to modify the address. So the sender on layer 2 is different. Because the address is different, the address cannot spend the USDC C2 has. That's why they use address aliasing for contract. All right, let's continue. After we emit these events, the layer 2 sequencer uses those events to generate deposit transactions on layer 2 to build the layer 2 blocks. And those deposit transactions are not retriable. They can only be generated once. If the transaction failed, you cannot retry that transaction. And here's the code path of the OP node and how they generate the layer 2 blocks. Let me show you a little bit. In OP, in this Optimism directory, this is a mono repo that contains a lot of folders, and it contains some projects that are used in Bedrock, and some projects are used in OVM v2, so it's very confusing. But all the components that are used in Bedrock will start with the OP dash prefix. So these projects are used in OP Bedrock. And this project may be used in OVM v2. So the OP node is the rollup node on layer 2. In this progress, it will read the, like I said, it will read the deposited transaction from layer 1 and generate a deposit transaction on layer 2 to produce a layer 2 block. And you can check it here. In the rollup node, you would need to fetch all the layer 1 events to build layer 2 block. You can check the layer 2 block build function. And in this function, there's a prepare payload attributes. That means we need to start building a layer 2 block, and this payload is used to build a new block, and the payload contains all the deposited transaction for this layer 2 block. So we need to fetch the receipts of a given layer 1 block hash. The epoch hash is the layer 1 block hash. So we call the layer 1 node through the API to fetch all the receipts of this layer 1 block. And the receipt is fetched through this receipt, Merkle Patricia try. And sorry, it's fetched actually from API. So the remote node fetched the receipt from its Merkle Patricia try and return the receipts. And if we gather all the receipts, we can filter out we can filter all the transaction deposit events in these receipts. So we need to derive deposit through these receipts. And you can see here, we just check all the logs in this receipt. Logs means events in a contract, and this event should be emitted in the Optimism portal contract. This address means the Optimism portal contract, and the event should be transaction deposit event. This is the transaction deposit event API hash. So we get all these transaction deposit events, and we use these events to build to generate a user deposit transaction. This is how the user deposit transaction got generated. And after generated, they would start to build a layer 2 block, and it contains all the deposit transactions, and the execution engine will execute those deposit transactions on layer 2. And the deposit transactions contains all these fields. So you can mint some ETH on layer 2, and you can call some contract on layer 2. That's how it works. And let's do some tests on Gordy. Here I have a test account, and I want to send a call to the Optimism portal contract. All the contract address I already recorded in this Notion page. So in layer 1, we have a Optimism portal contract. The contract address is this address. So here we call this address, and we call deposit transactions. And the argument is the address we want to call on layer 2, and the second param. Let's see, what's the second param? Second param is the value you want to call with this transaction. So if you specify some value, this value will goes into the mint field in this deposit transaction. So if you send some ETH to this Optimism portal contract, your ETH will be minted on layer 2. And the third parameter is the gas limit. Its creation is that it means that if you want to create a contract on layer 2, and the data is the data in this transaction. So here we send this is 0.1 ETH, and we want to send to this address. I think this is my address. And the data, we can just specify whatever data you want. So we just send some random data. Sorry. Oh, I don't have. Oh, I don't have ETH in this account already. All right, never mind. Someone transferred my Gordy ETH. So I don't have ETH to use on Gordy. Oh, but I already yeah, I got wrecked. I already tried it 7 days ago. But here you can see if I send 0, sorry, this is the value. I only see 0.01 Ether to another address. And this is the transaction on layer 1. And you can see in this transaction, we are sending to the Optimism portal contract. We can see here. Yeah, this is the Optimism portal contract. And the values we send is we want to call some address on layer 2, and we send some value to layer 2. And after this transaction got executed on layer 1, and after some time period, a transaction will generate automatically on layer 2 from the same address on layer 1. Because I'm using a EOA, we don't have to do the address aliasing, so the from address, the sender address is the same on layer 2. So we check here, this is the same address, and these 3 transactions are all deposited transactions. You can check the gas fee to ensure that it's a deposited transaction. We don't charge any gas on layer 2 because you already paid gas on layer 1. You have to pay gas on layer 1, so we don't need to charge gas on layer 2. And these transactions are generated automatically. The first transaction I sent to myself with some ETH. Yeah. And these 2 transactions also send some ETH to other addresses. You can also call some contract on layer 2. For example, if you want to call the professional protocol on Optimism after Bedrock, I think current version, in the current version, they also have deposit transactions. So if you want to call professional protocol on layer 1, you can send it to the deposit fee contract on layer 1, and you can call the contract of perpetual protocol to maybe you want to close a position in, for example, if the optimism is down and you have some open position in perpetual protocol and you want to close them because you may get liquidated because the price moves, but the layer 2 is down. So you can call it from layer 1. The advantage of doing so is that when the layer 2 is up again, your transactions will be included in the layer 2 block firstly, because deposit transactions are prioritized to be included in layer 2 block. So you have the chance to block close your position first before the liquidator liquidates you. Yeah. But remember, the deposit transactions are not retriable. That means if the transaction failed, you may have some funds locked on layer 1. If you want to send some value to, the value means ETH, if you want to send some value to layer 2 address and the transaction reverted, your funds will be locked on layer 1. Because if you call this function, you have to send the same amount of ETH to this Optimism portal contract. Let's say if you want to send 0.1 ETH to a layer 2 address, if the transaction executed successfully on layer 2, this amount of address will be minted on layer 2. But and this ETH amount will be locked on the layer 1 contract, and it got minted on layer 2. So you have the same amount of ETH on layer 2. And also you can send it back through withdraw. We'll talk about withdraw transaction later. But if this transaction executed failed, the ETH on layer 1 will be locked in this contract. So you have to remember this is not retriable. You have to make sure the transaction got executed successful. And we'll talk about the withdrawals. Withdrawals are just like the deposit is a cross-domain transaction, is the transaction initiated on layer 1 and executed on layer 2. Withdrawals are the same, but with the opposite direction. Withdrawal transactions are initiated on layer 2 and finalized on layer 1. But the process is a little bit different. For deposit, we can initiate a transaction and you got executed like 7 minutes later. So you won't take too much time to be executed on layer 2. But for withdrawals, we have to wait for 7 days to be executed on layer 1. So you have to wait a very long time for withdrawal transactions because we need to ensure that you're not cheating, your state root is correct, and all the transaction results are correct. And the withdrawal process is that someone on layer 2, a user on layer 2, call a contract called L2 to L1 message passer contract and call this initiate withdrawal function. And you can specify the target you want to call. You can call yourself on layer 1. So you can bridge your ETH on layer 2 to layer 1 by calling yourself. And the amount of the gas limit for this transaction and the data. And you can also use a value in this transaction. So you can send the ETH back to layer 1. In this contract, there will be a little bit technical. In this contract, they will generate a withdraw hash from the params you provided. So this hash is to ensure that you are executing exactly the same params on layer 1. So they generate a hash and store this hash in the contract storage called send messages and set it to true. Let's see how that works. Check. And if we call initiate withdraw, it's very simple. We just generate hash by using the params you provided, also include the message value. So you can send some value from layer 1 to from layer 2 to layer 1. After we generate the hash, we just save this hash in this contract storage. This storage slot is a mapping structure that maps a hash to a Boolean, and we set it to true. You can ignore this event. It will not be used on layer 1. That's all. It's very simple. After we initiate a transaction on layer 2, the proposer should submit the state root of layer 2 and the storage root of this contract to layer 1. So the proposer is run by sequencer. As I said before, they have very confusing names. It's actually the output submitter. Output submitter will submit the layer 2 state root to layer 1 in a contract called layer 2 output oracle. But this process not only submit the state root, it also submits the storage root of the contract, of this L2 to L1 messenger pass storage root. Why we need to storage root, I'll explain it later. And they submit to the contract on layer 1 called L2 output oracle. And after the state root is submitted, maybe we need to wait for a couple of minutes or one or 2 days. It's also possible. After that, we need to prove the state on layer 1 is correct by calling the function in the layer 1 contract optimism portal, prove withdraw transaction. So how do we prove it? We need to prove that on layer 2, in this L2 to L1 message passer contract, in the storage of this contract, and there would be a transaction withdraw hash, and the key is hash, and the value should be true in this storage root. In this storage slot, sorry. We can prove this by using the storage root submitted by the proposer, because the storage root is also a Merkle-Patricia trie, so we can prove it in the contract. So this contract, so in this contract, it needs to prove that it need to ensure that this withdraw hash is actually exist in this storage, and the value is true. So we can ensure that the layer 2 contract, the layer 2 storage is actually existed on layer 2, but we prove it on layer 1. The storage root is like what I said here. We have a storage root for every address of a contract. So if we have this storage root, we can prove that a key is in this root, and the value is what we want. Let's take a look. Layer 1, and we call this prove withdraw transaction to prove that the withdraw hash we want is actually set on the layer 2 contract. So we generate the hash again. And here we get the slot key, the storage slot key in the storage Merkle Patricia trie. And this is how Solidity encode the storage root. So we encode the slot key of this mapping here on layer 1, and we have this key, and we need to know the value is true. True is 1 in the slot, and 0 means false. So we can prove this by using the storage root. So this is storage root submitted by the OP proposer, and we have some proofs to proving that this key is set to 1 in the storage Merkle Patricia trie. If we can prove it, in this contract, it was saved in a proven withdrawal, so that we can make sure the withdrawal hash is already initiated on layer 2. So how do you get the withdrawal proof? Optimism proposer already proposed the storage root, so you need to have the proofs to prove that a key is in this Merkle Patricia trie. And there's an API called in the Ethereum node, both on layer 1 and layer 2, called, I think it's called get proofs. Yeah, you can call this API to get the proof of a storage in a Ether account. So the parameter is which storage root you want to approve. You should provide the address of the contract, and you want to prove which key you want to prove that it exists in this contract. In this API, they will return the proofs you needed to prove that the key value is actually stored in this Merkle Patricia trie. And after we prove that, we need to wait for 7 days because the storage root may be wrong. We need to wait for challengers to challenge this state root or the storage root. In fact, we don't need to. Technically, we don't need this storage root because if we have the state root, we can prove that some storage root is in this state root Merkle Patricia trie. But they also submitted this storage root for convenience so that we can save some gas. We don't need to prove it again. So we may need to prove that some key value is in this storage root of a contract on layer 2. So after 7 days, we can ensure that someone actually initiated a transaction on layer 2 that he wants to call address on layer 1. Then we can, anyone can call this finalized withdrawal transaction to call the target on layer 1. So this is different from the deposit transaction. It actually called from this contract. So that's layer 1. We have this Optimism portal. And layer 2, we have this L2 to L1 passer. I'll just call it passer here. So user initiated withdrawal in this contract. And after the OP proposer proposed the storage root in the L2 output oracle, we can prove that the withdrawal hash is stored in this contract. We can prove that by calling the portal contract. The portal contract will fetch the storage root, and you also need to provide the withdrawal proofs to prove that the key value is actually stored in this layer 2 contract. And after 7 days, this transaction can be relayed on layer 1. Let's say if you want to call address A on layer 1. So we can call this finalized withdrawals of this layer 1 contract, and the layer 1 contract will call the target you want. And you will also provide the data, which is the message if you want to call. And if you have some ETH you want to send, you will also send the ETH to this address. So if this is your address, let's say you deposited some address to layer 2, and you want to send it back to layer 1, you can use this process to send to layer 1. You just initiate a transaction. Let's say there's a 0.1 ETH. So the ETH will be sent to this contract, and after 7 days, 0.1 ETH will be sent on layer 1 to your address. So you withdraw your ETH from layer 2 to layer 1. This is the details of how they withdraw ETH. But actually, you don't have to withdraw. You can just call contract on layer 1. It's okay. Some security concerns, they use safe call function to ignore the return data, because some attacker may use a malicious contract and return a bunch of data on layer 1 and consumes a lot of gas on layer 1. So you can ignore this return data, because when we relay a transaction on layer 1, we don't need to know the return data. And there's a gas limit for the transaction to be relayed on layer 1. In Arbitrum, there isn't a gas limit. You can check this article about the design differences here. And this security researchers thinks that there are some issues for Arbitrum because there isn't a gas limit. Some malicious user may use a lot of gas on layer 1 and causing the relayer a lot of gas spent. And remember that withdrawal transactions are also not retriable. I think they want to be symmetric for withdrawals and deposits. So it's also not retriable. So you can call this finalized transaction once. If the transaction failed, you cannot call it again, because the withdrawal is already failed and your fund will be locked. You cannot withdraw your fund. And there are actually some bugs that attackers can intentionally make the call fail and to lock users' fund. You can check the Sherlock audit of the Optimism Bedrock. There are two high issues. The two high issues are all related to the lock funds by using the withdrawal transaction to make the transaction failed, and because it's not retriable, your funds will be locked. If you're interested, you can check it. And because the transactions are not retriable, this can be considered as low-level API provided by Arbitrum that developers typically do not use. Because if you accidentally make the transaction fail, your funds may be locked. So next, we'll introduce the cross-domain messengers. The cross-domain messengers are built on the low-level API provided by the deposit and withdrawal. And they make the message passing retriable in the cross-domain messengers, so that you don't have to worry that a transaction failed and you cannot replay it again. So the cross-domain messages can be replayed from on layer 1 or layer 2. And it's built on the low-level deposit and withdrawal transactions. And there are a pair of contracts for the message passing, the layer 1 cross-domain messenger and the layer 2 the cross-domain messenger. The message passing is pretty simple. If you want to pass a message from layer 1 or layer to layer 2, or from layer 2 to layer 1, that means you want to call a target on the other side of the chain, on another chain, and you have some message for this transaction, and you have a gas limit. You can also have some value to send to another chain. You can call this send message function. This function is both available in the layer 1 and the layer 2. So you can call a target on another chain. And on the other chain, you can get the message sender by using the X domain message sender function of this contract. You can check the details in this contract. And if it's a layer 1 to layer 2 message, because the sender may be a contract on layer 1, they will do the address aliasing. So you need to undo the address aliasing on layer 2 to make sure the sender is correct, if you want to ensure that sender is actually what you want. And if the related transaction failed, the user can manually replay the transaction by calling the relay message function. Here's how it works. For layer 1 to layer 2 message, firstly on layer 1, user call this function. Instead of calling the Optimism portal contract directly, they call this messenger contract to send a message. And in this contract, it will calculate the gas limit needed, this transaction needed, and call the deposit transaction. This is what we mentioned above in the deposit transaction, because the messenger also uses deposit transaction. And the deposit transaction will generate an event like we talked before. And a transaction will be generated on layer 2. And in this event, the target address is the layer 2 cross-domain messenger. So if you want to call a target on layer 2, the message sender actually generate a deposit event to call the layer 2 messenger contract. And here it actually calls the layer 2 relay message function. And the sequencer will generate a deposit transaction on layer 2 to call this contract. So actually in the low level, it's the layer 1 cross-domain messenger contract called the layer 2 cross-domain messenger contract in the deposit transaction. And then on layer 2, the deposit transaction is generated. And like I said, it calls the layer 2 cross-domain messenger and call this relay message function. And in this relay message function, it will help you to call the target you want. Call this target you set in the layer 1 send message function. So in the relay message function, it will direct the call to the target you want, and it will record the result is success or failure. If the relay transaction failed, you can replay it again by manually calling the relay message function again. So you can, if a relay message failed, you can call it again to replay the transaction on layer 2. And here's an example how other projects use this mechanism. In the chaining, they have a Optimism sequencer uptime field contract, which is a Oracle contract that reports the Optimism sequencer is up or down. and they update this contract through a layer 1 address. So they actually send a cross-domain message from layer 1 to layer 2 and update the sequencer status on layer 2. So in the layer 2, he has to get the actual sender from the cross-domain messenger, like I said, the cross-domain message sender function, and to ensure that it's a valid sender on layer 1. So this is the layer 1 to layer 2 message is quite like the deposit transaction, but they added a retriable message on it, so you can retry the failed messages. And for layer 2 to layer 1 messages, it's pretty much the same. User call the contract on layer 2, send message function on layer 2. And in the low level, it actually needs to generate a withdrawal transaction. Like I said before, it calls the L2 to L1 message passer and initiate the withdrawal and save the withdrawal hash in the storage root of this contract. And then we need to prove that withdrawal hash on layer 1 after the proposer submit the storage root and state root in the layer 1 contract. And we prove it. And we wait for the finalization period. And the relayer, anyone can be the relayer. So there may be a relayer run by Optimism team. So the relayer finalized the withdrawal transaction, and the transaction is actually calls the layer 1 cross-domain messenger relay message function. And in this function, you will actually call the target you want. You specified in the layer 2 call. So they will call the actual target address with the message. And if the message failed, you can replay it again. So it's pretty much like the withdrawal transactions, but you can retry those transactions. But you have to wait. You also need to wait 7 days for the finalization. It's pretty much the same. And then we move on to the bridges. Like I said, you can bridge ETH by using the deposit withdrawal or use the cross-domain messengers. You can bridge ETH to another chain or withdraw ETH from layer 2 to layer 1. But you cannot bridge ERC20 tokens, or you cannot bridge NFT tokens. So they build some standard bridge for ERC20 and ERC721. They call standard bridge. So there will be 2 pair of contracts on layer 1 and layer 2. So this standard bridge is used to bridge ERC20 tokens. This is the contract on layer 1. This is the contract on layer 2. And this is the same contract used to bridge NFT tokens. And under the hood, they use the message passing mechanism I mentioned before in this slide. So they use the message passer, and the domain messenger actually use the deposit and withdrawals. So this is pretty much like this picture. If you want to bridge some ERC20 tokens, you can call this bridge to bridge your tokens to layer 2 chain, and under the hood it will call the cross-domain messenger, and the cross-domain messenger will call the Optimism portal to generate a deposit transaction, and the deposit transaction we call this layer 2 cross-domain messenger and relay message function, and it will call the layer 2 standard bridge. So this is the process how you mint how you bridge a ERC20 token from layer 1 to layer 2. So there are multiple calls through here. Yeah. And before bridging from layer 1 to layer 2, you have to create the remote ERC20 or ERC721 contract. on layer 2. For bridging, you have to create those contracts, and that means you have to register those remote contracts on layer 1. So you create by using the factory contract on layer 2. This a token, let's say USDC on layer 1. On layer 2, we don't have USDC, so we create another USDC contract on layer 2. And we register mapping that this address maps to this address. And someone may create another USDC contract on layer 2. It's okay. So we have USDC 1 and USDC 2. There will be 2 mapping. And you can bridge your USDC to this first address, or you can bridge it to the second address. That's all fine. And you can bridge back to the layer 1 tokens. It's all fine. So you can create any number of ERC20 tokens on layer 2 that maps to a layer 1 token. It's fine. But actually, we always use one address because it would be confusing if you use too much you use too much addresses. And the bridging address is very simple. If you understand the process of message call, bridging is actually lock your tokens on the layer 1 bridge for layer 1 to layer 2. You actually lock your token in this contract. You lock the token in this contract, and you send the message to layer 2. And the message contains what contract address you want to mint on layer 2. So you lock your USDC here, and you specify another USDC contract on layer 2. And let's say you locked 100 USDC here, and you will mint 100 USDC on layer 2. And if you want to bridge back, and the layer 2 bridge will burn those USDC on layer 2. They will be burned. And you also use the cross-domain messenger to initiate a withdrawal transaction. And then the withdrawal transaction will be relayed after 7 days on the layer 1 through this process. And the layer 1 bridge knows that you burned some USDC on layer 2, and it will give back the 100 USDC to you. So this is the bridging process for ERC20 tokens. It's pretty simple to just use the cross-domain messages. And I will not give too much detail about this because it's quite simple. So here we have the deposit withdrawals and cross-domain messengers and bridges, so that we can bridge any assets, including ERC20, ERC721, and we can call contract or address on another chain by using the cross-domain messenger. We have these all features. And here we have some process that need to ensure the safety of the layer 2 system. The first one is the batcher. Batcher is used to submit the layer 2 transactions to layer 1, so that all the transactions on layer 2 will be available through the layer 1 API. So we can ensure that data is available and the data integrity. Layer 1, the OP batcher do so by read those transactions on layer 2 by, like I said, in the block header, we have the transactions list. We can read all the transactions in this Merkle trie in a layer 2 block, and then the batcher submits those transactions as core data to layer 1. So the batcher is pretty simple, just generate the transaction to submit those data to layer on the data so that we can save some gas on layer one. Here are we have some terms that are called batches and channels. A batch is all the transaction contains in a layer two block, and batches are aggregated into channels. So a channel contains multiple batches. That means断掉了。Since it's recorded, let's use English. We only have three people here. We only have three people here. Let's be faster. I will continue. So the batcher submits the transactions to layer one by using aggregation and compression. So they compress the channel. And since the channel may be too big, they split the channel into channel frames and submit those data to layer one through the batcher transactions. So we can get all the layer two transactions from layer one because batcher submits those transactions to the batch inbox address on layer one. And the batch inbox address is just a EOA address on layer one. You can check it here. This is the batch inbox for Gordy. It's just a EOA address. It's not a contract. And this is the batcher always submitting the layer two transactions on the Gordy Optimism to this address. And in this transaction, there are a lot of binary data because the transactions are compressed before submitted to layer one. All right. And we have the proposer. Proposer is used to propose the layer two state to the layer one chain. Proposer can get the layer two state through the Optimism output at block API from the OP nodes. So it works like here. This output submitter is the proposer. It gets the state root from the rollup node, and rollup node fetch the state from guest, and the state root will be submitted to layer one contract. It actually is this contract. Layer one output oracle, and also the storage root. Like I said before, the storage root will be used to prove that withdraw transactions from layer two to layer one. And we have to trust the proposer here. It's just a EOA address in Optimism Bedrock. We have to trust that it doesn't provide or submit the wrong state on layer one. If it submits a wrong state, someone can maliciously steal your font on layer 2. So if we have a fault-proof system, we can challenge the state root or the storage root and prove that it's wrong. So we can rebuild our layer 2 chain. All right. I will not talk too much details about this this channel or batches data format. You can read those in their specs docs. And layer 2 use this API to craft a transaction and submit the state root on layer 1, so that we can verify the layer 2 state is correct. And if we have a fault-proof system, we can prove that the state root is wrong or right. And if the state root is wrong, the proposer will get slashed. Next is the sequencer. Sequencer is actually the role that produced the layer 2 blocks. It just produced a block every 2 seconds, and by calling the execution API, like I said, the sequencer is the red part. It runs a rollup node that every 2 seconds, it will call the engine API to produce a new block. And in this engine API, there may be a lot of OP node in the layer 2 network, and they will sync the transactions submitted by user through the transaction pool. So when the sequencer start to produce a block, the OP gets the execution engine will collect the transactions in the transaction pool and produce a layer 2 block, a new layer 2 block on the layer 2 chain. And this layer 2 block is what we call a unsafe block in layer 2, because the transactions are not submitted by that submitter to layer 1. So for this unsafe layer 2 block, it can be propagated through the OP node by transfer the payload of the layer 2 node to another rollup node. So this rollup node get the payload of the unsafe block and produce a layer 2 block here. So we have the latest layer 2 block in our execution engine. All right. Here's how they implement the sequencer in the OP node. Since we only accept the blocks produced by sequencer. So if someone mocks a sequencer and he says that I am the sequencer, you cannot trust him, because the sequencer should sign the payload by using the private key. So we only trust the data submitted from the sequencer. So we need to verify the data by using the signatures signed by the sequencer. Okay, we have all the features of a layer 2 system. We have the proposer to propose the layer 2 state, and we have sequencer to produce layer 2 blocks, and we have batchers to submit layer 2 transactions on layer 1 so that all the data is available. And we have these bridges, messengers to do the cross-domain transactions. So for now we have all the features that needed for layer 2 system. But we missed one thing, is the fraud proof. In OP Bedrock, they will use a component called Canon to do the fraud proofs. For now, it's not implemented, but will be included in the future upgrade by using Canon. And Canon is developed by a talented developer called George Holtz. and it's an on-chain interactive disputing engine that implemented the EVM equivalent for proofs. It's half that, half MIPS. It's very difficult to understand. I think Canon is the hardest part of the layer 2 system. So this Canon will be compiled to MIPS instruction. MIPS is another instruction set other than x86. So it's Go code that compiles to MIPS instructions, and in this Go code, they runs a EVM, and they also emulating a MIPS machine and running the compiled Go code. And the Go code is run in EVM. It's very weird, sounds like. So the Canon is very tricky and hard to understand. I'll make it simple. We don't need to dive into too much details about the Canon because it's too hard to understand. If you're interested, you can read the code. The Canon is used to do the interactive fault proof. Like I said, in OVM v1, the fault proof is non-interactive, but now using a non-interactive fault proof, you need to have OVM in EVM. It's very hard, and it will be not EVM compatible. So they have to use another mechanism to do the fault proof. It would be interactive. Interactive means that we only execute a single instruction on the layer 1 contract instead of the whole transaction. In the whole transaction, there may be hundreds or thousands of instructions, and it will all be executed on layer 1. But for interactive fault proof, we only execute a single instruction in this transaction. And it's interactive because there are two parties in the fault proof system. The one is challenger and another one is defender. They will need to find out which instruction they disagree on. So we just replay the single instruction on the on-chain contract. We don't need to execute the whole transaction. So firstly, we need to find out the instruction we disagree on, and then we replay it on layer 1. Right. So this is how Canon works. Canon has a GAT in it, so the Go Ethereum client in it, but it removes the networking part. So in Canon, the GAT is called mini-GAT. The mini-GAT doesn't contain any networking part, like P2P networking or block mining. It just used to execute a transaction in the EVM environment. So by using the mini-GAT, it is a minimum modified subset of GAT. So there will no networking and no mining. And we compile this mini-GAT to MIPS instructions, and we execute this MIPS code on a layer 1 contract. And we need to find, because this is a interactive fault proof, we need to find out a single MIPS instruction that the challenger and the defender disagree on the memory. I'm sorry, this is disagree. But find a single transaction that these two parties agree on the memory, but disagree after that step. So we execute the step after this step these two parties agree on, and rerun this single instruction on chain. Mini-GAT is compiled into MIPS instruction because it's easier to write on-chain MIPS interpreter. So there will be a on-chain MIPS execution environment, on-chain MIPS VM written in a contract. There are only 400 lines. The canon contains mini gas, like I said, this is a gas implementation that removes the networking part. And the MIPI code is used to compile mini gas to MIPS binary. And they have a component called MIPS EVM to emulate running the minigas in a MIPS environment, because we use PC that runs ARM instruction or x86 instructions. We have to have a runtime to run the MIPS instructions. And there will be a MIPS VM contract on the layer 1 chain to execute a MIPS instruction. And because it's executed on chain, we have to manage the memory of this instruction, because since the instruction may need to read some data from memory. So the memory is actually not the memory in EVM. It's actually a contract to read from. So we have a MIPS memory contract to manage the memory MIPS used. And we have a pre-image oracle for MIPS VM. I'll explain the pre-image later. It used to, and the MIPS memory contract Merkleized the whole memory of the program to Merkle-Patricia trie, so that we can prove that the value in the memory is correct. And there's a challenger contract to disputing the state root and implementation of the challenge game. The challenge game starts with two parties, challenger and defender. So the defender is the OP proposer that proposed the states of the layer 2 chain, and if others can run a rollup node to be a verifier, and if they find a state root is not correct, they will be the challenger in this game. And they will deploy the challenge contract on layer 1, and the contract owner will be the defender, and there will be a start state. It is actually a root of the Merkle-Patricia trie of the memory, of the MIPS memory. So they need to find out which instruction they disagree on. They need to find out an instruction they agree on, but after that instruction, they disagree on the memory layout of the MIPS program. And the MIPS memory is Merkleized to MPT tree, and here's what MIPS memory layout looks like. It contains all the instructions that are needed in the program. So all the instructions in the minigas will be placed in these sections, and there may be some data, heap, and stack in the memory, and there are some reserved space in the memory layout. And we access the memory by memory address. So we can think of memory as also a key value database. The key is the memory address, and the value is the data stored in this address in the memory. So we can Merkleize this key value mapping to a Merkle-Patricia trie, to a MPT, so that in this MPT we can ensure that the data is correct. Because when MIPS is running, it is running in on-chain in a contract. When it needs to access some memory data, it will query the MIPS memory contract, and the MIPS memory contract includes a MPT that contains the memory data of the MIPS program. Also includes all the instructions. So you can the MIPS the MIPS program read the instructions and execute it. Because it's compiled into MPT, so the instructions must be correct. So you cannot run a wrong instruction in the MIPS VM on chain. So both parties need to isolate the first instruction they disagree on by using a binary search approach. And they need to rerun the single instruction on layer 1 in the MIPS VM to find out who wins the game. After this instruction, the state becomes another state, and if it is the state the challenger specified, the challenger will be win, and otherwise the defender wins. And the mini-guess is very tricky. Mini-guess is written in Go, and it can be run on chain, and you can also run it off chain. And for a program, we need to read data from I/O. Typically, we read data from disk, read data from network, and we read data from system environments, etc. But if mini-guess is running on-chain, how does it get the data it needs? For example, if mini-guess needs to read a data on disk, in a Solidity environment, there isn't any disk. How do we read data from disk? And if we need to read data from network, how do we read data from network? It's very tricky. We have this pre-image oracle. Because in Ethereum, almost every data reading is a key value based. Like I said, in the block header, we have some state root, Merkle Patricia, try. We have the storage root. We have the transactions root. We have the receipts root. All this data are stored as key value based in the StateDB. StateDB is a key value database that stores in the disk on the disk. And the key will always be a hash of the value. So in the ETH, we all read all the data by using the hash of the value and read it from the key value database. And we need a pre-image oracle on-chain to provide the data we want. The pre-image works like this. For hash function, we give it some input, and it will give us the hash result. What the pre-image means is that pre-image is the input value of a given hash result. It works like this. We give it a hash result, and it will give us the input of the hash result. So it's like a reverse function of the above function. Why do we need this? Because, like I said, almost everything in Ethereum is key value based, and the key is the hash of the value. So when mini-guess needs to read a value in the StateDB, he will provide the key. The key is the hash of the value, and he can get the value from the key value database. When mini-guess runs on-chain, he also needs to read those data. So how does the mini-guess read it? We have a pre-image oracle on-chain that provides those data through this function. So when mini-guess runs on-chain, he wants to read a value like address A. So he provides the key is a hash of A, and he wants to get the value stored in this key. When it runs off-chain, it just fetch this value from database. But when it runs on-chain, this hash value will be redirected to the pre-image oracle contract, and the pre-image oracle contract will provide the value. So this is how mini-guess read data and the contract. It's very tricky. So pre-image oracle is a function on chain that provides the value of a given hash, and you cannot provide a fake data because the key is the hash of the result. So we can verify that the input is that the return data is always correct by using the hash function, because if we hash it, it would be the key. So in this pre-image oracle, the challenger or the defender has to provide the data that mini-get needed. And so that mini-get can read all the data it needs. And like I said, the mini content should be correct. It is ensured by the hash function. And in the mini-get, they just hooked some function calls to fetch data from the pre-image in this two function. Like it wants to read data from the state DB. It will be redirected to call the pre-image oracle. And if it runs off-chain, it will be compared to x86 instructions and runs off-chain. The pre-image oracle just proxies the request to upstream its node. So it actually fetch the data from other nodes when it runs off-chain. And it will write those data as pre-images on the disk, so that user can submit those pre-images to the on-chain pre-image oracle contract, and then we can run the on-chain. Since we already submitted all the data we needed for MIPS instruction, so when the MIPS instruction run, I'm sorry, this is wrong. So the MIPS instruction runs, it actually read the data by using the pre-image oracle. There's a trick that they use the reserved memory space in the MIPS memory layout. So they use some space here to save the hash. Like I said, they save the hash here, so that we can know that we want this instruction want to fetch pre-image by using the key of this hash. And the pre-image oracle contract, in the pre-image oracle contract, user have to submit the value of this hash. So the value is here submitted by user, and the value will be stored in the memory layout in this Merkle-Patricia tree. Like I said, this is a Merkle-Patricia tree in the contract, so they stored the return data in another space in this in another stress in the reserved space. So the MIPS instruction can get the data it needed. And this is very tricky. You can read the code here that it actually calls the pre-image and writing to this address to save the hash and reading the result at this address. And this is implemented by using the contract function. So this contract function can know that MIPS instruction is reading some pre-image, and the hash is saved in this memory, and the MIPS memory can provide the pre-image and saved at this address. So MIPS can read any data from the key value database. And for memory reading, because memory is compiled to or localized to MPT, so user also has to provide all the data that in the memory that a MIPS instruction needed, because it's compared to an MPT tree. You cannot provide fake data, because we can prove that all the data using the state root of this MPT. And the initial memory state is submitted when deploying the change contract. And so the initial memory state must be correct. We need to trust that initial memory state is correct. And then all the memory states will also be compared to MPT, and we can prove that all the data is also correct. For the initial memory state, when the program starts to run, they don't have any data in the heap or in the stack, so it's empty. And they only have some instructions. These instructions are the MIPS instructions that compiled from the mini-gas. So all the mini-gas instructions are here. So we have this memory layout, and we compile this to MPT, and we provide this MPT state root as the initial root when we start the change game. And for MIPS to running, we also need some initial input, because when the challenge game starts, challenger and defender are disputing the state transition from block N to block N+1. So we need to have some information from block N and information from block N+1. The mini-gas needs to know the block hash of the block N and the transaction try of the block N+1. We can fetch this data from off-chain mode and save it to pre-image oracle. And if we run on-chain, we can, in the challenge contract, we can get the hash of these values and save the, like I said, this is the input hash. We can get those values and save the input hash in the contract. So the mini-gas knows the input hash, and it can read the input from the pre-image oracle. So mini-gas can get all the data it needs, and it can rerun the MIPS instruction. And if the state is the state provided by the challenger will win, and the defender will be slashed. So Canon will be used to, for now, the Canon is just a POC project. It can only be used to verify the layer 1 block state transition, but we need to use it to verify the layer 2 state transition. So there are a lot of works to do in Canon. It needs to be integrated with the OP node and OP gas. For now, the mini gas is just integrated with layer 1 gas. So it has to be integrated with layer 2 gas so that we can replay the instructions in the layer 2 state transition. And that after that, it can be used to used for the fault proof system of layer 2. And actually, Canon can use to verify any MIPS programs on chain. So let's say if you have a program that you want to run it off chain, you have any program, maybe this program is written in Go, and you can compare this program to x86 or to MIPS. And in off-chain mode, we run it in x86. And we can submit the result to layer 1 contract. There's a layer 1 contract. And we can verify the result of the program by comparing it to MIPS and using Canon to verify the MIPS instruction is correct, as long as we compile all the data structures to a Merkle-Patricia try, so that we can use the pre-image oracle. So the Canon can be used for other projects, not only a layer 2, like for example, this is a gaming process. So we have a game that runs off chain, but the result is submitted on layer 1. You can also submit it to layer 2 so that we can verify the results by using Canon on layer 1 or layer 2. So it's very cool. All right, that's all. Well, we take too much time. It's very long.